Hello, children.
Hello, teacher.
Sit down. Yeah. Today we have a physics lesson. Так, Lisa, what's in your picture?
I see my outfit.
Well done. Vadim?
I see the idol. What would it include?
Katya?
In my picture, I see a flower that relates to pressure, volume, and temperature.
Good. Vika?
I see in the picture the interaction of gas and electrons.
What do you think is the name of our lesson? Katya?
Ideal gas and the provisions of the molecular kinetic theory.
Vika?
Molecular kinetic theory and its experimental substation.
Great, good job. The topic of our lesson, ideal gas, the basic equation of the molecular kinetic theory. Open your notebooks. The 20th of December the 20th of December. Ideal gas. Ideal gas. The basic equation of the molecular kinetic theory. What do you think is the purpose of our lesson? Write the purpose of our lesson on the stickers and put stickers in the basket of ideas. basket of ideas.
Solve problems of this book.
Get acquainted with the concept of an ideal gas.
Write on standpoint and write on gases.
Solve problems using the equation of molecular kinetic theory.
Good job, well done. I suggest you fill in the table KWL chart. The first column is what you know about this topic. About this topic. Let's watch the video.
Hey, it's Professor Dave. Let's talk about ideal gases. Let's recall our definition of a gas as the phase of matter where atoms of substance are in motion and filled or contained. If we make a couple simplifying assumptions about gases, we can make some easy predictions. Those are that, 1, particles of a gas are dimensionless points in random motion, and the identity of the gas is irrelevant. Could be anything. And 2, that the particles don't interact apart from elastic collisions, bouncing off one another like balls on a pool table. These things aren't completely true, but they make the math easy and surprisingly accurate, so these kinds of samples are called ideal gases. When examining an ideal gas, we want to be able to discuss 4 variables. 1, pressure. This is the force the gas is exerting on its container, or rather, how much the particles are hitting the sides. 2, temperature. This is the amount of heat energy available to be transferred into kinetic energy of motion. The higher the temperature, the faster the particles move. 3, volume. How big is the container? And 4, moles. How many particles are there in the container? So, how many particles, how big is the container, how fast are the particles moving, and how often do they hit the sides? As it turns out, these variables depend on one another in interesting ways that have been formulated into laws. Let's look at a piston. While keeping the moles and temperature the same, in other words, the same number of particles moving at the same speed, if we compress the volume, the pressure must go up. The particles will be hitting the sides more often because there is less distance to travel to hit a side. That means that pressure and volume are inversely proportional. If one goes down, the other goes up. This is expressed in Boyle's law. P1V1 equals P2V2. If we double one variable, we have to cut the other one in half in order to keep this equation valid. Volume and temperature are also related. If we have gas in a balloon and we heat it up, the particles will move more quickly. In order to keep pressure constant or hit the sides with the same frequency, the volume will have to expand. This means that volume and temperature are directly proportional. If one doubles, the other must double. This is expressed in Charles' law. When we do calculations with temperature, we must always use an absolute temperature scale called the Kelvin scale. 1 degree Kelvin is the same magnitude as 1 degree Celsius, but 0 Kelvin is absolute zero, the lowest temperature possible, a complete absence of heat energy. This helps us avoid weird mathematical issues that would arise if we were doing a calculation involving a negative or 0 temperature. To get Kelvin from Celsius, just add 273. To go the other way, subtract. The combined gas law is like a combination of Boyle's and Charles. Avogadro says that equal volumes of gases at the same temperature and pressure contain the same number of molecules. Specifically, that 1 mole of ideal gas occupies 22.4 liters at standard temperature and pressure, regardless of the identity of the gas. Lastly, all the variables correlate in one equation called the ideal gas law. This also contains the gas constant R, which makes these calculations intelligible in our man-made units. There are a number of values for R depending on the units, but we will predominantly use this one. This equation is useful when we aren't looking at a change, but just to know the values of all 4 variables at once, like in this case. We could know the pressure, temperature, and volume of a gas, and quickly calculate how many moles of particles must be in the sample. So if you were looking at a sample of gas, and you have 3 of the 4 variables, you can solve for the 4th using the ideal gas law. If you are given some initial conditions, as well as some final conditions, you can use one of the other laws to find the other information. Just plug in what you know, and solve for what you don't. Let's check comprehension. Thanks for watching, guys. Subscribe to my channel. Thanks for watching, guys. Subscribe to my channel for more tutorials. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.
What did you see, Katya?
I saw the gas molecules accumulate the entire volume provided to them. Maybe cautiously without stopping their movement. Also, the gas molecules create pressure on the vessel wall.
Yes. Who else? Lisa.
I saw that the gas molecules increase their speed as the temperature rises. As the volume decreases, the gas pressure increases.
Well done. Who else? Vika.
I noticed on the video that when the gas is heated, its volume increases. There is a temperature that is minus 200 and the 73 degrees, which is called absolute zero.
Well done. Good job. Let's split into 2 groups. 2 groups. First group. Second group. Read the text and discuss important issues. Make a poster based on this text. You have 10 minutes. Evaluated by criteria. Criteria. Make a poster based on this text. First group, please.
An ideal gas is a gas force interaction between molecules is negligible. The main differences between an ideal gas and ideal gas. 1. Ideal gas particles are special bodies of very small size, electron material forms. There are no intermolecular interaction forces between the particles. Particles collection are absolutely realistic, rarefied gases that behave like an ideal gas. Why does the gas pressure get on? Test on the map.
mathematical correction are absolution errors. Who? No.
Well done, good job. Evaluated by criteria. Foster evaluation criteria. Foster evaluation criteria. First group.
Mobility on the material, yes, 1 ball. Discipline, yes, 1 ball. Availability, yes, 1 ball. The ability to isolate the main, no 1. Visibility, yes, 1 ball. Creative originality, yes, 1 ball. Longness of our group, yes, 1. No 1 ball. More children and symbols than words, yes or no.
Well done. Good job. Second group.
Knowledge of the material, yes, 1. Discipline, yes, 1 more. Availability, no, 1 more. The ability to isolate the main, yes, 1 more. Visibility, yes, 1 more. Creative originality, yes, 1 more. Involvement of all group members, yes, 1 more. More characters and symbols than words, yes, 1 more.
Thank you. Well done. Sound your 2 stars and wishes. Sound your 2 stars and wishes. First group. First group.
The second group managed to reveal everything on this topic well done. The only negative is that I would try more words in future.
Yes. Second group.
We like everything the first group will done. Everything worked out for you. The whole topic is well done.
Yes. You are wonderful children. Perfectly copied in the test. I suggest you to consolidate the material study test. We check the test on our give ourselves an assessment. Answers to the test. Vadim?
7.
7 ball. Vika?
8 ball.
8 ball. Lisa? 8 ball. Katya? 9 ball. Complete the table KWL chart. Learn. Complete the table. Write down your homework, paragraph number 6.3, literates 3 and 4. Literates 3 and 4. The lesson is over. Goodbye, children.